In the previous lecture, I described faint, diffuse phenomena that you can see in a dark sky while you're on a camping trip or something like that. And that includes the Milky Way and the zodiacal light and great auroras if you're sufficiently far north or south, like this one right here. These phenomena don't require any binoculars, any telescopic aid at all. But you can get a more detailed view of certain objects if you use binoculars or a telescope. They have a very narrow field of view, so you can't see wide areas of the sky with binoculars and telescopes, but you can see individual objects much more clearly and in more detail. So in this lecture, I'd like to describe the use of binoculars and telescopes. Binoculars and telescopes collect more light, making objects brighter and allowing you to see fainter stars in the sky. They also magnify objects, making them look bigger or closer. They also provide a clearer view, and I'll discuss that in more detail when I talk about professional large telescopes later on, but they sharpen the image. One thing to note in understanding how binoculars and telescopes work is that the rays of light coming from distant stars are nearly parallel. Previously, when discussing crepuscular rays, I had told you that the rays of light from the sun, which is 93 million miles away, are nearly parallel. They're coming in like this from a point so far away that you can't really tell that they're diverging. Well, stars are even farther away than the sun, much, much farther away than the sun. So the rays are parallel. They are not diverging the way they do for objects that are close to us. This is important to understand when looking at how a telescope or binoculars work. Binoculars and telescopes work by bending or refracting light from objects using a lens or a mirror. Let's consider a lens first. Here's a lens made of glass with the incoming parallel beams of light. First from one direction, those are the black ones, and then from another direction, those are the blue ones. You can see that the light is bent by the lens to a common focus right there. And light from different directions in the sky gets brought to a different focus, but in the same plane, something called the focal plane. And the focal plane is one focal length from the middle of the lens. So now let's look how light brought to a focus by a lens in a so-called refracting or bending telescope can be used to get a clearer, more magnified view of an object. There's the primary lens that brings the light to a focus, and then an eyepiece is used to view the image and to magnify it. So if we take a refracting telescope like this, take the lens cover off, open it up, the light can come in, it gets bent by the primary lens, gets brought to a focus, but there's nothing at this particular focal plane. No photographic emulsion or anything else was put there, so the light keeps on going. It goes through another lens called the eyepiece lens, and this allows your eye to see an image of the object. So there's the ray tracing diagram through a refracting telescope. The combination of the primary lens and the eyepiece lens is what gives you the amount by which an object is magnified. If you take lenses having different focal lengths, and here I'm adjusting the focal length of the primary lens, you can see that the image down below gets smaller or larger depending on the focal length of the primary lens and hence on its distance from the eyepiece lens. Quantitatively, the magnification is given by the focal length of the primary lens divided by the focal length of the eyepiece lens. Notice also that the image is inverted. Similarly, I can change the focal length of the eyepiece lens and watch the effect it has on the image. It gets magnified more or less depending on the relative focal lengths of these two lenses. If I increase the diameter of the main objective lens, I can make the image look brighter because more rays of light are being captured by a bigger lens than by a small lens. See, so the object got faint when I made the lens small. The refracting telescope was invented by Dutch opticians in the early 17th century, but their models were essentially toys. Galileo heard of the design and made a better working version of a refracting telescope. And he showed the Venetian Navy that you could see ships far away coming up over the horizon. And the Navy was very impressed by this because they could see ships coming in long before they actually approached. And so they gave Galileo a rather large salary to continue building telescopes for them. A few of Galileo's early telescopes are shown here. They were much better than the initial Dutch versions because they could be used to make serious astronomical observations and to give very clear views of ships and other approaching objects. But they were very small telescopes. Now, if you take two of these small telescopes and put them together, two refracting telescopes and put them together like this, you get a pair of binoculars. Actually, that's a bit of a funny name, binocular, because why would you call it a pair of binoculars when, in fact, this is one binocular? But anyway, that's the way it goes. Here's a pair of refracting telescopes put together, and you look through them like this, and you can see objects magnified and appear brighter. So you're just using a couple of simple refracting telescopes. In movies, the common depiction of what you see through binoculars is something like this. They have you seeing a different part of the image through each of the different refracting telescopes, or the monoculars, if you will. That's actually not the way things work. When you look through a pair of binoculars and you have them properly adjusted, your eyes actually see the same field of view through each of the monoculars, and then your brain puts them together to give you one clear image. You do not see two different images like this, juxtaposed next to each other. A view of a cluster of stars through binoculars is shown here, and you can see what I just said, that you get a single circular field of view. Now there's a problem with refracting telescopes that Newton recognized, and that is that the lens brings light of different colors to a different focus, that is, to a different distance from the lens. Violet light is brought to a shorter focus than green light, and red light is brought to an even longer focus. So if your eye were here, the green light would be in focus, but the violet and blue would not, nor would the red. So you would get a fuzzy image of the object, and this is called chromatic aberration. Chromatic stands for color. The Scottish mathematician James Gregory proposed a different design that eliminated this problem. But Isaac Newton was the first to actually build a working model of a reflecting telescope, this other design. And the reflecting telescope, instead of using a lens, uses a mirror to collect light and bring it to a common focus. Here is a diagram of a mirror, a shiny reflecting surface, with light rays coming in parallel from a distant star and being brought to a common focus. And all of the light rays, regardless of color, get brought to the same focus in the case of a reflecting telescope, so you don't have chromatic aberration. Now, if your head were right here at the so-called prime focus of a reflecting telescope, your head would block most of the incoming light rays, especially if your head is bigger than the mirror itself. Then it would block all of the incoming light rays. So here's a reflecting telescope with the open end staring up at the sky up here. If I were to look into it, positioning my eye at the prime focus, look at that, my head would block all of the incoming light, so there'd be really nothing to see. So you need some sort of a design that eliminates that problem. That design comes in one of several forms. One design, a Cassegrain reflecting telescope, has a hole in the primary mirror and a secondary mirror which is smaller than the primary mirror. That secondary mirror would block some of the incoming light, but not all of the incoming light. Okay? So if we open the lens cap, or the telescope cover, light rays coming from a distant star can bounce off of the primary mirror, reflect back to a secondary mirror, and then bounce off of that and go through a hole in the primary mirror, finally coming to an eyepiece lens and then to your eye. Certainly some of the light rays are being blocked by the secondary mirror, but if the secondary mirror is small relative to the opening of the telescope, or to the primary mirror size, then most of the light rays are not being blocked, and you simply have a slightly fainter image than you would have had you not had that blocking of some of the light rays. You don't get a hole in your image. If you're looking at Jupiter in this case, you don't get a hole in the image of Jupiter caused by the secondary mirror. And that's because every part of the primary mirror forms a complete image of the object. Every part forms a complete image. So by blocking some of the light rays, you've simply made the image a bit fainter than it could have been. You have not created a hole in the image. There's another design that's easier to make. Grinding a hole in the primary mirror is a little bit tough. Suppose instead that you tilted the secondary mirror at an angle like this. Then light coming in from the primary could bounce off of the secondary perpendicularly and off to the side of the telescope where your eyepiece could be placed. A diagram of this, called the Newtonian reflecting telescope, is shown here. The rays are coming in, they hit the primary mirror or the objective mirror, the light rays reflect off of the objective, hit a secondary which is tilted, and that secondary, in its tilted way, deflects the light sideways to the side of the telescope where the eyepiece and your eye can be located. So in this telescope, this is precisely the Newtonian design. The primary objective mirror is down there. Light comes in from the stars, goes through the tube, hits the primary mirror, comes back up, hits a tilted secondary up here, which deflects the light in this direction. And you can look through the telescope like so. So it's very easy. You can also have a little finder telescope that allows you to identify the broad region of the sky in which you're looking in order to find Jupiter or whatever object that you precisely want to focus in on. You will notice that when we looked through a refracting telescope, the image was inverted. Now, if you're using a telescope to look at birds or people or buildings, that can be kind of distracting. So, a lot of telescopes come with an erecting lens. An erecting lens is simply another lens that inverts the image, making it look upright. And you can attach that to a telescope. Now, if you're looking at celestial objects, up and down doesn't really make any difference. You know, Jupiter upside down or right side up looks about the same. But if you're looking at, say, birds or deer, or if you're a nature photographer and you've got a camera attached to your telescope, you'd like to have these things right side up. So here is my son looking at a bird through a refracting telescope that has an erecting lens. The bird just happened to be inside a cage in someone else's house, but so he's not spying on anyone there. But it is interesting that you find refracting telescopes in lots of homes, sort of looking at other homes, and in tall office buildings, looking into the windows of other tall office buildings. So one of the more common uses of telescopes, at least the small kinds that you can buy in department stores, seems to be for sort of spying on other people. You can even see these things on large structures like the Eiffel Tower. At the top there's a platform which has a bunch of refracting telescopes. And here is a famous astrophysicist viewing buildings or people or whatever they're doing through a telescope at the top of the Eiffel Tower. But astronomers want to use telescopes to look at celestial objects. So at this point, let's go back and turn our attention to the sky. First, we'll consider the kinds of objects that are easily seen with a pair of binoculars. Knowing the constellations allows you to find interesting objects to look at easily. For example, going back to the summer triangle, which I introduced in the previous lecture, it consists of Vega, Deneb, and Altair. A photograph of it is shown here. So if you go from Vega to Deneb and keep going in that same direction, you will run across an interesting object, Messier 31, M31, another galaxy, and it's in the direction of the constellation Andromeda. Here is a picture of Andromeda taken through a telescope no more powerful than a typical pair of binoculars. You can see this fuzzy little streak next to the stars of the constellation of Andromeda. But instead of being just a few tens of light years away, like these stars, this is a galaxy of billions of stars about 2.5 million light years away. So with a simple pair of binoculars, you can see quite well the Andromeda Galaxy, the nearest large collection to our own. There it is. It's 100,000 light years across, 2.4 million light years away, and you can get a good view of it through a simple pair of binoculars. Another way of finding the Andromeda Galaxy is by finding the